Hello everybody, it's Mrs. Pound and I'm back with the second video for Chapter 12 on gases from BJU Chemistry's 5th edition. So today we're going to be talking about Section 12.2, the gas laws. So our objectives for this video will be to predict the behavior of gases, calculate changes in the pressure, temperature, and volume of a gas, and explain how the gas laws work. So the first thing we have to know is that there is a condition called STP. This is standard temperature and pressure. So whenever you see STP, you are going to know that the standard temperature is 0 degrees Celsius, which is also 273 Kelvin, and 101.325 kilopascals, which is also 1 atmosphere. And one note to make is that whenever we do any of these calculations we're going to talk about today in the gas laws, we always do them in Kelvin, never Celsius temperatures. So Celsius temperatures used in gas law problems must be converted to Kelvins. The reason for this is because we do not want to have negative numbers. Now, the first law is Boyle's law for pressures and volumes. And this law explains how pistons work. And remember, we said in the last section that if the pressure is increased, we will decrease the volume of the gas. And if the volume increases, the pressure lets up. Or if we let up on the pressure, the volume increases. So when one goes up, the other goes down. And so we have the equation P1V1 equals P2V2. What this means is the gas will start out at an initial pressure and volume. Those are P1 and V1. And then one of the conditions will be changed, and we can calculate what the other condition is. So if we start out with a certain pressure and volume and we alter the pressure, we can calculate the new volume. So let's take a look at how that is done. A problem we might see using Boyle's law is a gas in a cylinder occupies 455 milliliters at 103.35 kilopascals. So here we see the initial volume, V1, and pressure, P1. How much space does the gas occupy if we increase pressure to 113.48 kilopascals? So we have our second pressure, and we want to be able to calculate the volume because volume is how much space something takes up. So the first thing I like to do is write down what I know and what I want to know. So we know the initial volume is 455 milliliters. The initial pressure is 103.35 kilopascals. The pressure that it is under increased pressure. So 113.48 kilopascals, and we're after the second volume. Now, looking at this, we know that when pressure goes up, volume should go down. So my prediction is it will be a smaller volume, using what we already know. Let's see if it works. So I write down my equation. P1V1 equals P2V2. I put in my substitutions for my P1, my V1, my P2, and V2 remains as a variable because that's what I'm after. Now, I cannot get my answer this way. So using algebra, I have to divide both sides by 113.48 kilopascals. So I show that work here. Now, I am just adding things in, so you don't have to rewrite all these numbers each time, just to show you the progression. So you just have to add each new thing on all of these problems. So when I rearrange, I get this. Now notice kilopascals cancels out, leaving me with milliliters. So I have volume as an answer. So that's also a check to see if I've done it correctly. Do I have the correct units when I cancel everything out? And so the correct answer for volume is 414 milliliters, and my prediction was correct. The volume went down. Now, another gas law is Charles's law, and Charles's law deals with temperatures and volumes. And this explains how hot air balloons work. So this explains why when we increase the temperature of the air in a hot air balloon, the volume increases and then it becomes less dense and rises. Now, Charles's law has to do with volume and temperature, and it's V1 T1 over T1 equals V2 over T2. So we're dividing here. And remember, volume and temperature have direct relationships. So when temperature increases, volume increases. When temperature decreases, volume decreases. So a problem dealing with Charles's law is one like this. A sample of gas occupies 3.15 liters at 25 degrees Celsius. So here I have my initial volume, V1, and I have T1. Assuming that pressure is constant, how much space will it occupy at standard temperature? So I want to know V2, and they do, in a roundabout way, give me T2 because we know that standard temperature is 0 degrees Celsius or 273 Kelvin. So I write down what I know. I know the initial volume, 3.75 liters. I know T1, 25 degrees Celsius, but remember, I can only do these problems in Kelvin, so I add 273 to it to get 298 Kelvin. And then T2, I know that the standard temperature is 273 degrees or 273 Kelvin, and we're looking for V2. I write down my equation. V1 over T1 equals V2 over T2. I plug in my numbers. 3.75 liters divided by 298 Kelvin equals V2 divided by 273 Kelvin. Now I want to get V2 by itself, so I need to multiply both sides by 273 Kelvin. That rearranges my equation to this. Kelvin cancels out, leaving me liters as my volume unit, which is good. And when I do the multiplication and division, I get that V2 is 3.44 liters. So my temperature went down, and so my volume went down, which makes sense from what we already know. Okay, the third gas law to you with dealing with temperature, pressure, and volume is Gay-Lussac's law. And his deals with temperatures and pressure. And again, remember, these have a direct relationship as well. If one goes up, the other goes up. This explains why air pressure in a tire is higher after the tire heats up and why a hairspray can explodes in a fire. So we have P1 over T1 equals P2 over T2 for our equation. And these do have a direct relationship. When one goes up, the other will go up. So a problem we might see dealing with Gay-Lussac's law is before Molly began a car trip, she measured the air pressure in her car tires and found that it was 221 kilopascals at 18 degrees Celsius. After 2 hours of driving, she found that the pressure had increased to 248 kilopascals. What was the new temperature of the air in her tires? So we write down what we know. We know the initial pressure is 221 kilopascals, the initial temperature is 18 degrees Celsius, and the final pressure is 248 kilopascals. So if pressure increased, we expect temperature to increase. So again, we write down what we know, the initial pressure, 221 kilopascals. We cannot leave temperature as 18 degrees Celsius. We have to add 273 to it to get 391 Kelvin. And for the pressure, 248 kilopascals. So we're looking for the second temperature, T2. For this problem, I start with my equation, P1 over T1 equals P2 over V2. I substitute in my values. 221 kilopascals over 291 K equals 248 kilopascals over T2. Now, for this type of problem, I'm going to cross multiply to rearrange the equation. So when I cross multiply, I get 221 kilopascals times T2 equals 248 kilopascals times 291 kilopascals. I still have to get T2 by itself, so I then divide by 221 kilopascals on both. So when I rearrange my equation, I get 248 kilopascals times 291 Kelvin divided by 221 kilopascals. I cancel out the kilopascals and I am left with the unit of Kelvin. So that's good because I am in temperature. And so when I do the math, I end up with 327 Kelvin, which I must subtract 273 and get 54 degrees Celsius. So I can see that, in fact, the temperature of the air in the tires did go up. Now, we can combine all of these gas laws into the combined gas law. And this is on the last page of your reference tables. And if you look at it, you do not have to memorize these equations because you can just get all of them out of this combined gas law. And if something is constant like temperature, you just don't put it in your equation. You just drop it out, or volume or pressure on any of them. But you must drop both of them out. And the reason you can do that is because if they're the same on both sides, when you do the math, they'll cancel out anyway. So you do not have to memorize anything. This is on the last page of your reference table. You just have to know that you don't necessarily always have to use all of the quantities. You can drop one out of the equation. So a problem using the combined gas laws might look like this. A sample of gas has a volume of 3.6 liters at 106 kilopascals and negative 15 degrees Celsius. What will its volume be at STP? Remember, STP is 0 degrees Kelvin and 101.3 kilopascals. So we have V1, which is 3.6 liters, P1, 106 kilopascals, as I was given in the problem, T1, negative 15 degrees Celsius, which I add 273 to get 258 Kelvin. My pressure is 101.3 kilopascals because that is standard pressure. T2 is 273 Kelvin. Remember, these are on the front page of your reference tables if you forget. And V2 is what I'm looking for. So I write down my equation. P1 V1 over T1 equals P2 V2 over T2. I substitute in my values that I wrote down before. 106 kilopascals times 3.6 liters divided by 258 Kelvin equals 101 kilopascals times V2 over 273 K. When I rearrange, it becomes this. I multiply both sides by 273 K and divide both sides by 101 kilopascals to rearrange to get this. Kilopascals and Kelvin cancel out to get liters. When I multiply across the top and divide by what's on the bottom, I get a volume of 4 liters. So that is the combined gas law. And like I said, you can take that apart and just use 2 of the quantities if you need to. The final gas law I want to talk about is Dalton's law of partial pressures, and this deals with mixtures of gases. This says that the total pressure of a mixture of gases equals the sum of the pressures of each individual gas, and those pressures are also called partial pressures. So an equation for that is P total equals sigma means sum of the pressures of little I means individual gases. And I just have the sigma sign there because it's as many gases as you have. If you have a mixture of 2 gases, it's just 2. If you have a mixture of 10 gases, you have to have 10 different pressures. We're not going to do any problems with this, but this is the importance of knowing this law. Chemists are unable to obtain accurate measurements of a gas that is collected over water because the process of collecting gas over water leads to some water vapor entering the gas sample. When this happens, wet gas is formed by water vapor mixing with the gas. So you have to be able to account for that extra pressure from the water vapor. Therefore, when collecting a gas by water displacement, we must remember to adjust for vapor pressure. So we're not going to do any problems with that, but it is something to be aware of. So our objectives today were to predict the behavior of gases, calculate changes in the pressure, temperature, and volume of a gas, and explain how the gas laws work. There will be one more video for this chapter.